Okay, so let's suppose we are issuing a trip command from IED1 to circuit breaker 1. Okay, so IED1 to circuit breaker 1, right? And message is obviously triggered by something happened in IED1. It detected some fault, so it needs to open that circuit breaker. So we need to send the message. And there is obviously no reliability service in this case, right? We talked about that this will be a goose message and there is no reliability service. So that means we have to do multicasting. Okay, but this is how the process will flow. Okay, in this case, we know these services, right? So client server communication goes through all the layers. Okay, whereas these ones only go through the link layer, Ethernet layer, and that's it. Then it goes directly to wherever it has to go. Okay, there is no reliabilities, there is no other services that are provided by these layers. There's nothing like that, because as we talked, if we try to do that, it's going to cost us time, which we don't have for trip commands, right? So ID1 is going to issue the trip command. Okay, so ID1 protection general operation, it's for circuit breaker 1, and then it goes to, the MAC addresses. Basically it appends, and that's it, nothing else, right? And then we have the same. So it basically goes through directly through the link layer. So this is what will happen. ID will issue the command, okay, for circuit breaker 1. It will go through this hub, has no intelligence. So it's going to send that information everywhere, okay, because it can't route. It has no idea where to go. So it will send to this ID, it will send to the switch as well. So whatever, is connected, it will. So this ID will receive it and it will interpret it, and it knows that it's not for it. The information is actually for circuit breaker 1. So it's going to just ignore that. Then it will go to the switch, okay? And because it's a multicast, it's a goose message, there is no information about routing. Although this switch may be intelligent, it can interpret if the routing information is there, but because we don't access that layer, so it's not going to go there. So this message will also go through everywhere. Okay, so it will go here, and through hub it will go to these two devices. Obviously they will ignore it because it's not for them. This HMI will ignore it. Here it will go to these places, they will ignore it. Eventually circuit breaker 1 is going to recognize that it's for it, this, because it has its MAC address, right? So then it's going to basically strip that information, right? And it will know that it's to open that circuit breaker, right? That protection is meant to open that. So this is how the circuit breaker will be opened. Okay, right? So, and depending upon, sometimes they have the MAC address, sometimes they may have only destination device ID, depending upon how you set it up, right, for recognition. But that's how it happens. So sampled values are similar. Okay, the only difference is, sampled values are transmitted continuously, whereas goose is only initiated by somebody, right? And also there is no multicasting, whereas in goose you can multicast, you can send the same message again and again, right? So let's say we want to transfer samples from ID1 to ID4, because same data can be used by ID4, for example, for differential protection, right? You need data from both ends of the line, right? So, and also there is no reliability service, no multicasting, right? So ID1 to ID4, right? So this is what will happen, right? So you start with the instant magnitude of voltage or current, whatever is, append the ID4's address, MAC address, right? And then you send that message. And same thing will happen here too. ID1 goes to both places. From the switch router, same, goes to all places. The only one that will recognize this is ID4, and it will strip that information out of, it will go in the reverse direction, basically. It will find the instant magnitude, right? So this is, again, very simple processes that happen. And then client-server communication, let's say we want some energy values transferred from ID3 to HDMI, okay? This is a reliable service now, okay? It's going to use all the layers, but each layer will add its own overhead, okay? And it will increase the message size. So ID3 to HMI, right? So this is, let's say we are doing the total bots. MMXU is the logical node for measurements, right? And this is the total bot value. And then HMI IP, okay? And then TCP will add its own overhead, okay? IP layer will add its own overhead, and then eventually the message will become very long, right? That's what will be transmitted. But it has now reliability services, routing available, and all that, right? So this is what will happen. ID3, because this has no intelligence, so again, it will go in all directions. But the switch has intelligence now because it has the information where to route it. So it will only route to HMI, and at HMI, it will be stripped, right? And eventually, you will get the value, okay? So very simple process, okay? Now, with these, you can do peer-to-peer communication, on the station bus, for example, devices can talk to each other through goose messages, okay? They can initiate any goose message they want, right? And you can share configuration data also using the same set, although we didn't talk about configuration, but you can. Actually, we have done some work where just by changing configuration data, we can change the nature of ID. Okay, there are two papers that we have written. This was the work we did for Hydro One, our transmission utility. So, for example, one of the IDs goes bad. Its functionality can be transferred to another ID or a spare ID. And you can do that through configuration. Because remember the logical nodes, because logical nodes are the ones that provide functionality to any ID. So if you can just change the logical node, then you can change the functionality. So logical node could be protection, measurement, breaker. So you could, rather than having a breaker, I can put something else in there, right? So you can actually change that, and you can do that on the fly, right? So, but you can share that information, and there are, this is what I was saying. Most of the substations have now. They have hardwired to IDs from the breakers or from the CTPTs. At the station bus, we have the IEC-61, but this is where we want to go also. Process bus also should be IEC 61850 compliant, and it should be networked. So then you can share all this information from anywhere with everything, right? So any possible architectures, you can have. So this is a star station bus which is connected in star, right? So these are hardwired, conventional, but this is your station bus, which is connected in star. You can connect in a ring bus. So any possible architecture that you can think of, or you can have a combination. Part of the station bus can be star, another part can be a ring, right? Here, you could have modern CTBT going directly to the relays, the sampled values, right? And then rest is all conventional. So you can have a combination of that, right? And this is breaker ID directly to the station bus. right? So any possible, combinations you can have, right? Depending on, and this is 2 process buses are there, right? Connected in a star. And then they are connected to the ring bus, which is your station bus, right? And right. So best configuration that you decide can be, yeah. You can, so it all depends how you configured your system, okay? So ID can be configured to receive data from only particular devices, particular IDs, so that it's not overwhelmed, right? So you can configure that. So that's configuring your communication. And the tool I was talking about, it will allow you to do that. Okay, so ID have a specific file, okay, which will define its capabilities, and also you can configure who can access the data from that ID. Okay, because you don't want to, every ID have access to everything. I think that will be too much. Although you can, but it probably is not very good idea. So you only decide, the few IDs you really need to share data, then you can do that. And that's why sometimes you divide the process bus also, right? Because you only need that type of data from those devices. So you divide them. So again, it's up to you. It's very flexible. Okay, this is why I say, we are, they are all unique in a similar way, right? So it's they're all following IEC 61850, but they're unique. You can have any unique combinations, right? And setting up this one doesn't take very long. With that tool, you can set up the whole substation, in few hours, compared to what they do now, right? With hardwired and so on. So this is the summary. So this is a little bit of additional information. I talked about the message types, uh, various message types that are there, right? Time, transfer time, and so on, whether it's critical or not, right? So, so those are again some of the. I don't have a map here. I think it may be somewhere another presentation. I have a map of the world where what countries have adopted IEC 61850. So the mandatory ones, where it's mandatory, India is actually one of those, where all the IDs, new IDs that are coming in must meet the IEC 61850 standard. China is again another one. And very interestingly, where this standard originated, it's not mandatory there. Canada, US, not mandatory. Although they are using it, but it's not a requirement for devices to be there. Europe, some portions, it's mandatory, but not everywhere. I don't have that map. It's very interesting map. But whether it's mandatory or not, almost everywhere it's being used. And not only that, I don't have the slide. It has been extended to other areas. So for example, DERs are now using that, okay, especially wind is using it. Gas industry has started using this one, okay. There are other applications, and they have made their own standard, because the data models we talked about, the ones I described are specifically for power substation application. But if you can extend your data model and add your own data models, then you can have the same concept for any industry. It doesn't matter, right? So, okay, so I think that's all I had for this one. What I want to do now, yeah, we can stop unless you have any questions on this. Everyone is okay? You are all IEC 61850 literate. Okay, great. Because remember this, we are going to be using this information later on. Okay. Yeah. So what I want to do is, there is a presentation. Oh, actually, we have to pull it out of my laptop. Let me see what is there. What was there? So we are going to talk about basic foundations of cybersecurity, and I will spend most of the time on public key infrastructure because um, all the standards we are going to talk about for cybersecurity, especially for substation automation, are using the PKI, okay, public key infrastructure. So it's important to understand the basics. And there may be some information that I will skip over very quickly, but we will. So this one, I think we already talked about. Dr. Bhalja talked about that, confidentiality, integrity, availability. So I don't need to repeat that. You know, why cyber attacks are important, don't need to repeat that. And then we talked about the common threats that are there. So I'm going to skip all that, right? Ransomware, phishing attack, uh, authentication. So this is where we will start. Encryption is very important for cybersecurity, but later on, I will tell you even there are threats to encryption right now, okay? Possible threats in the future. So it basically converts the readable data into unreadable data. We call it ciphertext, okay? And we obviously require a key to decrypt it and key to encrypt it, and data in transit. So there are two types of data, you know, static data, which is stored data. We need to protect that, as well as data in transit. Need to protect that also, and data at rest, right, which is stored in servers and this encryption and PKI is also the foundation for VPNs, which are very commonly used, okay, and secure messaging as well as secure storage, okay. So as I said, this is the fundamental to all cybersecurity solutions that are currently available, that are being used in industry, okay. So it's very important. So there are two types of encryptions. One is symmetric encryption, which basically uses a single secret key, okay, to encrypt, and you need to have the same key to decrypt, okay. So, and the common ones are, there are algorithms which we are not going to talk about the details of those, because as I said, that's a separate topic by itself. You know, what are the various encryption algorithms? Okay, I will show you some examples. I have written some Python code which I will run and show you how it looks like, right? So AES, Advanced Encryption Standard, and then DES. There are, you know, AES is very common, okay? And key distribution is a major challenge, as you can understand, right? If, you know, um, people got hold of the secret key, then obviously your encryption doesn't mean anything. They can get that. So this is the issue with symmetric encryption. And then we have asymmetric encryption, which is very commonly used now, okay? Where we use pair of keys. One is known as the public key, the other one is known as the private key, okay? So it will allow the secure communication over untrusted networks. You can do secure communication, and I'll give you examples. Later on, we will talk about it. So right now, with this presentation, we are doing an overview of the whole thing, okay? And it's used in digital signatures, okay? You can digitally sign a message, okay? And you will do that, you know, with your private key, but with your public key, anybody can interpret that message, okay? But nobody can change it. They can't change it. They can get it, interpret it, but they can't change it. And the examples of asymmetric encryption, RSA, ECC, curve cryptography, there are many algorithms that are used, and there are standards algorithms that are used. Actually, there is an organization in US that takes care of all these encryptions. Okay, you can actually come up with an algorithm and submit to them that I have come up with this encryption algorithm and submit to them. They will take a look at it. If it is good, then it becomes part of the standard, their standard. And right now, they have just done one which takes care of quantum computing. Okay, we will talk about that, the threats to some of these encryption methods. Okay, so what are the digital signatures? Okay, this is again, we will tie this all together through examples later on. Okay, so digital signature is a way to verify authenticity and integrity of a message document. It's like, you seal it and you sign it. Okay, so once you see it sealed and signed, you know it's authentic, and you can trust it. Okay, so as I mentioned, digital signature is created by sender's private key and verified with their public key. So everyone, think of the device, ID. They will have their private key and they will have their public key. Okay, and it will ensure non-repudiation. That means sender cannot deny sending it. That's another thing. If somebody sends some weird message and later on say, oh, no, I didn't send it, you can't deny that, because you obviously signed it, right? And it's very common in contracts, software distribution, and secure emails, and also secure messages that we will talk about, the digital signature. Okay, so that's the digital signature. Right now, all we are doing is understanding all these various, aspects of that. And as I said, we will tie this all together. Okay, and then how do you maintain all these keys? Every device has a private key and a public key, right? Senders have, how do you manage that? So this is managed by what we call public key infrastructure. Okay, so it's a system where we manage the digital keys, all these private and public key, and also digital certificates. That's another aspect. There are digital signatures and there are digital certificates. Digital certificates are also used for secure messaging. Okay, especially to set up a secure communication channels. Okay, let's say, and this is very well used in SCADA, for example. Okay, and we will talk about that. Okay, so what are various components of public key infrastructure? The various components, there is a certificate authority, okay, that issues and revokes certificates. Okay, and then there is a registration authority. We will talk more about these. Okay, there is a certificate database where all the certificates are stored. Okay, and I'll show you an example of a certificate, how it looks like. It's a standardized also. Okay, X.509, I believe. Okay, and then certificate revocation list. So you revoke some certificates, you need to maintain a list which certificates are revoked. Okay, so it's secure, sports secure email. This is where the SCADA, TLS, transport layer security. Okay, so it's mainly to set up secure communication channel. Okay, we'll use that. And it also supports digital signatures as well. Okay, so that's another aspect that we need to understand. So what is a digital certificate? What does it contain? Okay, as I said, it's a standardized document. Okay, it links a public key with an identity. Okay, so you have a private key, you have a public key, and also you have a digital certificate. Okay, so, and it's issued by a trusted certificate authority. Okay, everybody can't issue it. It's issued by a trusted. And what does it contain? Contains the public key. Okay, it certificates holders information. It also contains the expiry date, and it has the digital signature of the certificate authority, just to make sure that it's a legitimate certificate. Okay, so now we understand the digital signature. So certificate authority will sign this certificate with their private key, but anybody can verify that signature with the public key, with their public key. So they have certificate authority also has two keys, private key and public key, just like anyone else, right? So they can digitally sign this. So this is a digital certificate, okay? All these will come back when we talk about the standards and how we do the secure communication and so on. So get into, remember these things there, right? So this is what I was talking about, SCADA, Transport Layer Security, TLS, okay? It's a cryptographic protocol used to secure data in transit, okay? This is used in SCADA. So there were, I'm sure you heard about SSL, secure sockets. It basically replaced that. It's much more secure than that, okay? And it will provide the encryption, it will provide the authentication, integrity, and we use that in HTTPS. Every time you go to a bank, go do a banking transaction, this is exactly what happens, okay? They're going to verify the digital certificate, okay? That's how you will get in. And also VPNs and, email, secure email, and so on. Okay, as I said, we are going to tie this all together, give you examples so that you fully understand that. And then there are firewalls. I think we all know that. Okay, firewalls are mainly filter the incoming traffic and outgoing traffic based on the rules. They have, certain rules, and based on that, they will. Okay, so there are various type of firewalls. They are used in the power industry, but I think they are not 100% secure. They are another level of defense, basically. Okay. Um, and VPNs, I think we know that, right? Many of us are aware of that. Okay. It basically hides the IP address, and also it encrypts the traffic, right? It does the encryption. So this is mainly used, let's say an engineer is sitting remotely and they want to access, a substation computer remotely, right? So then, you can use the VPN for doing that, okay, virtual private network. So this is basically what we are looking at, the complete system. Firewalls, we will talk about the intrusion detection system in one lecture. Okay, what is that? And then network access control is there. Okay, this is important, security information and event management, right? So many utilities now have that. It basically tells you who is accessing what and what's really happening on your network, right? And then vulnerability scanners. This is where we will talk about auditing. I can actually, we developed a tool way back, many years back, when people were not even talking about that serious about cybersecurity, where we could run that tool and tell you how vulnerable your system is to, cyber attack. And where are the vulnerabilities? Okay, and they have these tools, Nessus and OpenVAS, that you can run on your system and find out where are the vulnerabilities in your system. Okay. Endpoint security, we talked about that. Okay, so it's at every level you have to provide that security, including your laptops, phones, tablets, and so on, right? And this is where the malware usually enters through, right? So antivirus, anti-malware, and so on. So this is, I think, we also use on our laptops, and companies, actually the ones who provide operating systems, they provide these type of protection tools for you. We'll talk about network segmentation. For power industry, this is extremely important. You segment your network into smaller zones, okay, so that you limit the spread of the threat, right? So that only one part of your system is exposed, even if it is under threat. So, and I'll give you some examples of that. right? We talked about intrusion detection. So it continuously monitors, and any suspicious activity it will report. Okay, there are various types. You can have a network-based, you can have a host-based. For example, well, current IEDs don't have the capability to host a intrusion detection system. Okay, so most of the systems are network-based. So at the network level, they will try. But I think the future IEDs, and this is where I think work can be done. So those are host-based intrusion detection system. So your IED itself will be able to detect intrusion. If right now there is nothing like that. So this is a layered defense, basically. So at every layer, you have to have that defense. That's what it is. Okay. So DMZ, demilitarized zone, is another one that strategy is used. I'll give you some example of that. Virtual networks, and then zoning. We talked about segmenting your network, and then redundant paths and failover. So you can have a redundant network. So if one network you think is being intruded, then switch over to your network, which is safer, right? So depending upon the criticality of your assets, you could do that, right? Demilitarized segmentation, yeah. Demilitarized zone. So these are the zones which are extremely important for you, okay? And you basically fortify them completely, right? I'll give you the examples later on. We will talk about that. What are they? How did you set it up? How did you determine what zone need to be demilitarized, right? And then zero trust security model. So this is again more from cultural point of view. So remember I talked about it's not the technology, it's also your cultural and management. That's extremely important to provide cybersecurity. This is more from cultural. Never trust, always verify. It doesn't matter who it is. The prime minister of the country comes, you don't trust. You say, we have to verify. Sorry, sir, we have to do this, right? This is more cultural thing, right? I hear stories when somebody, it's again cultural, nothing, where somebody important goes to the airport and they basically tell them, we have to check your bags. And they get upset. I'm very important person, right? Why are you checking my bags? So this is what it is, right? Never trust, always verify. That's what it is. So verify every request as if it is coming from a open network. So this is more cultural thing. Okay, so you will verify the identity, compliance, micro-segmentation, and so on, right? So policies and governance, this is more management side, right? So it defines the rules and procedures for data protection, key policies, right? More harder you make it, better your cybersecurity will be. Okay, so and then you have to have incident response plan, fully data classification policies, what is important, what is not important, classify them. Okay, actually NERC and some other standards actually want you to do that. Want to define what is important, what is the most critical, what is the least critical, and based on that, you provide the security, right? And that's where it supports the regulatory compliance, because now utilities have to be compliant with some regulations, right? So they have to start doing that. And this is the incident reporting plan, right? This is again very much management side. We are not going to talk too much about this given the time, but it's equally important. We are going to focus more on technology side, okay, in this course. So, for example, post-incident review. What really happened when an incident happened? Why it happened? Where was the weakness? And how did you fix that? Right? So, idea is to minimize damage and recovery time. Right? Training. very, very important, equally important. Training of everyone involved should be there, right? So that's another part of the management side, right? And data loss prevention, this is very important too. So you always back up, right? Even in our own personal lives, we back up our computers and say, in case I lose this data, I have a backup. I can restore that. I can tell you personally, it has happened to me. I was, somebody, jammed my computer, right? I think it happened through the university network, right? So they basically, encrypted my files and I think demanding money. And then I took it to our, IT people, and they had the backup data. They said, you will lose only 1 day work, right? We have everything back up. So they basically backed up everything, and that's it, right? So if I didn't have it, I probably have to pay them to get my data back, right? So data loss prevention, right? And so now everything is on cloud. So cloud security has become very important now, right? So key management is actually, we will talk about that in more detail, okay? And so it's really a shared responsibility between the cloud provider and the user also, right? Mobiles is another one, although we are not going to talk too much about that. But nowadays, smartphones and tablets, they are really for malware, theft, and spying. As they are everywhere, and there are so many cases we hear, that people got scammed via there because of the smartphone. They answered something, and right. So there are remote wipe capabilities that are there. Screen locks and biometrics are there, right? Uh, so, so compliance and regulation, there are, organizations which are required to meet the industry standards. And for power industry, it's no different. Now they have, you saw in the first presentation, all the compliance regulations that are coming up that has to be met now, right? So social engineering attacks, this one, and we have seen even in power industry, the blackmailing, right? So employee with, privileged access could be blackmailed, right? And they end up giving out the information, and then attackers use that information. So, but those are mainly the state actors, okay, not small cyber criminals who are only after money, but these are the people who are like spies. They are state actors, and now they're blackmailing people to giving them information, privileged information they have access to, so that they can do the cyber attacks, right? So password management is another. I gave you example of IDs, not changing the password. So that's another important thing, having change the passwords and management of it. But those are cybersecurity risk management. So this is where we will talk about auditing. Okay, identify, access, and prioritize your risks at every level in the power system. So identification will be through auditing, and and then accessing it. So you give a value to every possible scenario. You say, okay, I'm not very good at this, but what is the risk for me, risk level? Okay, so that's what. So obviously you will first go with the high priority risks. If you are just starting out, that's what will happen. Okay, and you have to conduct regular risk assessment. That's another one. Auditing has to be done regularly, because what happens is, let's say a patch comes, there was a security risk, a patch was provided, and this is what very common in utilities. They don't patch. And you know why? I have heard this from protection people. They say, as soon as I change the firmware or do something, my protection gets screwed. I don't want to take that chance, right? So they don't want to go to a newer version. So as a result, there are no patches done. Okay, so they are obviously vulnerable, and this is what cyber attackers actually use. Because they know, when a patch is provided, we know that this is a particular vulnerability, right? They know that, and they also know that everybody is not going to apply that patch. So they are going to use that to their advantage. Okay, so supply chain is another one. We quickly talked about that, where you have the contractors and you have the supply chain, because so many people are involved in this, right? So it's the third-party vendors and partners. And risk could include software and their own poor vendor practices. Okay, so utilities, what have to start doing is basically, looking at their vendors and, really demanding them to have proper cybersecurity, aspects within their own organization, right? So contractual security requirements should be there. And as I said, there were some cases where cyber attacks happened via them. A subcontractor came, connected their computer to the system, and through that computer, cyber attack happened, right? Because their computer wasn't secured in that case, right? Software development is another one. Okay, this is why we have these patches, right? Because when the software was initially developed, it wasn't cyber secure, right? Then they found they have to patch it, and so on, right? So that's another area, although it's not threats from current or former employees. Those are insider threats. Okay, sometimes that happens. A disgruntled employee can, uh, try to do the damage, right? So, and access control and employee training. Person has left the company 2 years ago. They still have access, right? So that happens. And so that means, you have to have proper access control there. As soon as they leave, so that's actually organizations sometimes are very poorly managed in that case. Employee is gone, they still have access, full access to everything, right? So penetration testing, this is where, the auditing part comes, and there are tools related to that. And, some companies, the ones, which are very highly critical companies, they actually hire the hackers, okay, just to find out where are the vulnerabilities in their system, okay, so that they can fix that, right? So yeah, so right now there are no matrices. This is another one, measure of performance. Um, although in research there are, people have proposed, and when we will talk about auditing, we have our own matrices that we used. Okay, so but you could use number of incidents detected in a year, time to respond to threats, past compliance rate, so all that. So you can use that as matrices, how well your organization is doing, right? So, but right now there is standards don't have that. They don't provide. Like we have power system reliability that you must meet 99.99%, right? There is nothing like that in this one. So that's another open area to work in, actually. Okay. So this one, I think we will talk about that. Encryption, quantum computing is actually big now. Okay. And it's very interesting. They stopped using symmetric encryption because the key distribution was hard. So they went to asymmetric one, right? They went to asymmetric one. But interestingly, with quantum computing, asymmetric one is the easiest one to, to break. So they are now going back to symmetric one, because symmetric one, depending on the length of the key, it will take a long time, even for a quantum computer to break, right? So, but they are trying to develop new algorithms now for encryption, which they call are quantum computer resistant. Okay. So, but those are again the future threats. But I think we are not even there. We still have a lot of work to do, even in the other area. I don't know when quantum computing will become available to cyber attackers, but but before that, we have a lot of other work. There is artificial intelligence being used, and research work is done in that area, where you could in real time, do the threat detection and response, right? So, and even, in the security tasks, it can help, right? Especially the ones that are very repetitive security tasks, okay? And you can actually set it up behavior-based anomaly detection, right? And used in malware. It's not, again, perfect, okay? But it's something that, can be used, and better than nothing, basically, right? And critical infrastructures, we talked about that. So I'm going to, so this is, again, very general for small businesses. Also, remote work. This is, again, people who are working remotely, they have access to, to the company computers and company infrastructure. So there we are people are using the VPNs and TLS, transport layer security, right? Education is important also. So again, um, you know, there are actually, I don't know, in utility industry, are they hiring specifically cybersecurity engineers? I'm not 100% sure how many utilities are actually have positions specifically for cybersecurity engineers. Maybe those who are in utilities can tell me. I'm not sure if there are positions specifically for cybersecurity, right? But irrespective of that, everyone should have some knowledge about the cybersecurity, right? So this is, again, best practices, updates, passwords, multi-factor authentication, suspicious links, which are, click on a link and you have the, right? Culture itself is important, right? So this was very quick overview, okay? Now what we want to do is we want to go back and look at more detail about the public key infrastructure, because that's what we will be using. And we will use some examples, and I have some software programs also. But before we do that, go there, any question? We will need to change to my computer now. Yeah. Maybe just hold on. Maybe I have that presentation here, but for programming, I think I'll need my computer. Yeah. So let's just go to, we can give 5. Yeah. So I have seen companies where they insist that they want to use their own server. So it all depends what type of data you have, what is its importance, right? And obviously you have to look at the cost and what expertise you have within the company. You know, if you feel that within the company you have expertise to set up your local servers and protect them and so on, right? And you have the means, economical means to do it and maintain all those, then I would say that's better. Okay. But if you don't, for example, for a small business, it's very hard for them to, you know, set up this whole infrastructure. Okay. They can use the cloud, but at the same time, as we talked about, it's a shared responsibility to maintain security. The, the cloud company will do their part, but as a user, you have to do your part as well. Okay. So for small businesses and small companies, they use cloud for them. And for the, you know, obviously bigger organizations, they're going to, you know, if they can afford their local servers and they have the expertise, they can do that. And that, in my opinion, is actually better. You are not exposed to outside. Only your internal people have access to it. Do is we are going to get into a little bit more detail about the public key infrastructure, especially cryptography. Okay, and we are going to talk about asymmetric because this is what's currently used, especially for, you know, power systems. Okay, also known as public key cryptography because it uses the two keys that we talked about. So there is a public key which is shared with everyone. Okay, and there is a private key which is kept secret by the owner. Okay, so everyone, every device in our case will have that. Okay, so how it works is that if someone wants to send a someone wants to send you a encrypted message, they will use your public key to encrypt it, but only your private key can decrypt it. Okay, so that's sending the message. Okay, so this one solves the one problem, the key exchange in the symmetric one. You know, previously they used symmetric cryptography, and you have to exchange that key and keep it secret at both ends. So this one doesn't, you only keep your private key secret, right? So, and common algorithms we talked about, okay? So you encrypt a file using somebody's public key, they can decrypt it using their private key, they can sign a message with their private key, and you can verify the signature using their public key. Okay, so that's the digital signature. Digital signature is opposite to the sending the message, right? So encrypting the message, you use their public key and decrypt it. They decrypt using their private key, but when you are signing a message, you sign it with your private key, and anybody can verify with your public key. Okay, so that's what happens with digital signature. So it's like this, you know, right? So real world analogy is like a mailbox, right? Mailbox. Okay, imagine a mailbox. Mailbox is locked. Okay, you give the key to put in the put mail in the public key, right? And then only you have the key to open the mailbox. So just imagine a mailbox with a slot. You know, anybody can put a message in there, but only you can open and take it out, right? So this is how it happens. It's actually very simple process, right? So the main uses of this method is encryption, okay? And the goal is to only the intended person can read the message because you have to decrypt it using your private key, right? Only you are the one who are going to read, okay? So Alice wants to send a secret message. Bob gives Alice his public key, okay? Alice encrypts the message with that public key, which is available to anybody, but only Bob can decrypt it using their private key. So that's one use of it. Okay. The second use is digital signatures. As I said, it's opposite. In this case, make sure the message came from someone and it wasn't changed, right? So what happens is, writes a message, signs it with their private key, okay? And I'll give you examples. How does it look like, when the message is signed, right? And Alice will receive the message and verify the signature using Bob's public key, which is available to anyone, right? So it's opposite. So what happens is, then it verifies that Bob is the one who really sent it, and there was no tampering on the way with the message, because if you tamper message, it will not verify the signature. Okay, signature verification will fail. And again, I've written few small programs. I'll show you how that will be done. Okay. So why it's useful? No need to share secret keys, just like symmetric cryptography. Okay, it scales easily. You don't need a separate key for every person. Okay, and it enables secure communication between even strangers on the internet. Okay, and this is what is used when you go and log into your bank. Okay, this is exactly what they use, right? So there is another analogy, padlock, just for understanding. They are far apart, and Alice wants to send Bob a message. Alice and Bob are far apart. So what will happen? Bob sends an open padlock, which is the public key, right? Which is available to everyone. Okay, and that padlock is unique to Bob and can be only opened by his own key, which is the private key. Okay, so Alice will put her message in the box. Okay, and once locked, only Bob can open it, because Bob has the private key. Okay, so that's all that is. Okay, so and then flip it for the digital signature. Okay, so Bob will lock the box with private key. Okay, anyone, Alice can open the box using Bob's public key, and if it opens, that proves that Bob is the one who locked it. So authenticity, remember the three pillars, right? And integrity. Okay, so that's how it will be. So this is again just the same thing. Okay, so let's take a look at a little bit more on the encryption, and I will use a very simple example that you can do by hand. Okay, but later on, as I said, we have a program. I will show you how that will work with the program. It's obviously much more complicated than that. Okay, so let's say we have device B signs a message. Okay, device A need to verify it using B's public key. So devices A and B both have their public key and private key. Device B have public key and private key. Okay, so we will use the RSA, algorithm. Okay, so we pick small numbers. Okay, let's say modulus n55, public exponent 3, private exponent 3. So Bob's public key is 3 and n55. Okay, Bob's private key is 27 and n55. That's modulus. That's again part of the RSA algorithm. And let's suppose we have a message. Okay, hi. Okay, and what usually happens is the message's hash is created. Okay, so the hash of message, let's say hi is 5, for example. Okay, so now device B will sign the message. 5 message will be signed, and they will use their private key. So what is their private key? Private key for B is equal to 27, right? 27 is the private key. So what will happen is, this is the algorithm. Okay, signature will be created, which will include 5 raised to the power 25 mod 55, whose value will become 25. Okay, and again, these are small numbers. I'll show you the real signature. Okay, when I run that program, okay, using RSA, it's actually much bigger and much more complicated. Okay, so B will send that 25, and out of that 25, A has to extract this, right? Because it's the signed message. Okay, so the original message and the signature is 25, right? That's what we have created. And by the way, how to compute that 5 raised to the power 27 mod 55? Okay, so it's very simple. Actually, you raise that 5 raised to the 27, divide it by 55, and whatever is the remainder is 25. That's how the algorithm works, RSA algorithm. Okay. So device A will verify the signature. It does two things. Recomputes the hash, which is 5. Okay, it doesn't know that yet, right? But it will use the public key to verify. Okay, so 25 was the message, 3 is the public key. Okay, mod 55, same thing. So that's 5. Okay, so what happens? It will, do the hash of that. So comparison, decrypted signature hash equal to 5, computer hash is also equal to 5. So that means signature is verified. Okay, because the message is contained. So you are not encrypting the message here. Okay, in real life, you will encrypt the message also. Okay, this message will be encrypted as well. So then A has to first decrypt the message and then verify the signature. Here, message is included there, just need to verify the signature in that case, right? So A is going to receive both message as well as the signature, which is 25. So they will verify that, right? So this is how verification of that. So signature is valid, that means, right? So if the decrypted signature hash is 5 as well as computer hash is 5, that means signature is verified. This proves that only B has the private key who could have signed this. So signature is valid. Message wasn't changed because the hash matches, right? And A didn't need the B's private key in this case, right? So this is about digital signature. Okay. So let's take a look at encryption and decryption, which is opposite to that. Okay. So what we want to do is device A wants to send a secret message to device B. B should be able to read it. Okay. A uses B's public key to encrypt, but B has to use the private key to decrypt it. Right? So it's opposite to digital signature, what we did. Okay. So same thing. Same, we will use the same public key and private key. So modulus, and this is the part of the algorithm. So B is E33, modulus 55, private key is 27 and 55. Okay, so A is going to encrypt the message. Okay, same message, hi. Okay, so modulus, the hash is 5. So encrypt the message using B's public key, which is equal to 3, right? So 5 raised to the power 3 mod 25, okay, which will be 15, right? 125 mod 55, right? Remainder is 15, right? Right. So that's so A will, this became the ciphertext. This is now the encrypted text. Okay, instead of 5, it's now sending 15, right? So 15 will be sent to B. Now B has to decrypt it using their private key, which is equal to 27. Okay, right here, 27, right? So they will do that. So 15, that was the message sent, raised to the power 27 mod 55 is equal to 5. And that is the original message, right? So this is how original message, decrypted message. So this is how the encryption and decryption works with the private key and public key, and the digital signature works with the private key and public key. Now, let's complete this whole thing. You can, I could have encrypted the message here, right? I could have encrypted the message and also signed it, right? So you could combine both that, right? So then you get the, authentication as well as, all three aspects of security you will get. And this is what they generally do. They will encrypt, sign it. At the other end, the other device will decrypt it and also verify the signature. Okay, so now we will talk about this. So now remember the goose message, right? Right now IEC 61850 has no security. So what they have done is, and we will talk about this in the standard, the goose message is now going to be signed, right? So once it is signed, at the other end, let's say circuit breaker receives the goose message to open the breaker. Now circuit breaker has to verify it's coming from a legitimate place and where it's coming from, right? So let's say ID1, let me just, we will talk about this in more detail, but since we are here, might as well discuss that, right? So let's say this is ID1, right? It's connected in the system, we talked about that, right, in our example, and this is your circuit breaker 1, right? So this one sends a goose message to trip this circuit breaker 1, right? So this, what will happen is this goose message, which is high here, is going to be signed by ID1. Okay, and how does it sign it? Remember, how does it sign? What key does it use to sign? Private key, its own private key, right? So ID will use the private key and it will sign this goose message. Okay, it may be to open the breaker, it may be to close the breaker, we don't know, whatever it is, right? So it arrives here at circuit breaker 1. Circuit breaker 1 is going to verify the signature using the public key of this guy, ID1. Okay, and if it verifies, that means signature is valid, then it will take the action. Otherwise, it will not take the action, right? So now just imagine a cyber criminal cannot do this, right? They don't have the private key of ID1. Okay, even if they got hold of the message in between and they changed it, right? This will not be able to verify it. It will not verify, right? Because the message is signed, it's all ciphertext, right? They will not be able to interpret it and verify. So the message will not verify. I'll show you with an example later on. Okay, so this is how they achieve, and we will talk more about the standard itself later on. This is just one example of what happens in the standard using this public key infrastructure, right? So this was small example. And now what you can do is two of you sitting next to each other can do this and exchange secret messages. Yeah, right? You can do all this, right? This is one algorithm. There are other algorithms, similar one, right? Yeah. Okay, so that verifies this. So this basically proves, we talked about that. Okay, so This is encryption, decryption. Okay, did we do this? Huh? Yeah, we done this, right? Yeah, I think this is again how to, rather than, when you have large numbers, we had like 5 raised to the power 27. Okay, you don't need to do that. Actually, there is a simplified way of doing it. You basically break it down like this. 5 raised to the power 27, you break it down. It's much more efficient way of doing the calculations. Okay, now the other problem is, remember the goose message, it has a time limitation of 4 milliseconds, right? It has to. So now you have added, actually, you are doing making a ciphertext, and you are also doing a verification. So you have added time. So that means these devices now have to have good amount of computation power. And this will be the problem with power utilities. They have these legacy systems which are there, which do not have these may not have these capabilities of doing it, right? So what do you do in that case, right? So for newer one, it's okay. You can, you can demand the manufacturer should do this, but for the existing legacy systems, it's going to be a problem. Okay. I think this is it for this one. Yeah, this is just, I will share this with you. So this is more efficient way of, computing. And this is what the algorithm does too, by the way. I have used small numbers. Obviously, they are larger numbers there, right? But you should try this by hand. That's all you learn. Okay, I will show you the programs maybe tomorrow. We may not have time today. We will run, because I want to run all the programs together, not half today and half. So we will do that. So one more I have. So we will talk about the certificate authority, how the public and private keys are managed, and who manages it, right? Actually, it's interesting. There are everybody cannot be a certificate authority. Okay, there are only certain organizations or designated organizations who have the public keys and private keys. Okay, all your Google, for example, they are a certificate authority. They have, when you connect to the bank via Google server, Google, right? So that's what they have, right? So I'll give you a few examples of that. Very quick overview of public key infrastructure. This is really the backbone. And even in our standards, we talked about the digital signatures, encryption, decryption using public key, private key. So that gives you an idea how it's done. But who manages and how it's done? What are the policies? What are the procedures for these public keys and private keys? Okay. So it's really a interesting system of hardware, software, people, policies, procedures that are used to create. You can create, manage, distribute, use, store, and revoke digital certificates and manage public key encryption. Okay, so that's what it's used for. Okay, so basically it's doing the same thing. It's allowing the parties who don't know each other, okay, identity, authentication, encryption of communication, and integrity. Right? We have seen that with those few examples, that's what we can achieve. So there is a public key, private key. We already know about that. Okay. So what are various components of the public key infrastructure? There is a certificate authority. Okay. It's a trusted third party that issues, validates, and revokes digital certificates. Okay. We haven't talked about certificates much. We will talk about them. Okay. Because as I said, in the transport layer security, we will use the digital certificates. Okay. So registration authority, okay, it verifies the user or organization before a certificate is issued. Okay, so those are all part of the public key infrastructure. So you and I can't go and register. Okay, they will verify whether we are a proper registration authority. For example, a bank can, right, do that. And then there are digital certificates, which is based on a standard X.509. Okay, it will contain the public key, not the private. Private key is with the owner. You never share that with anyone. Public key, owner's information, and certificate authority's digital signature, okay, will be on that certificate. Okay, so they will sign it with their private key, but you can verify that a digital certificate is authentic by using their public key, just like we did, right? And then there is a certificate revocation list, the revoked certificates, which are no longer trusted, okay? And then there are key pairs, public key and private key, they will maintain those, okay? Both public key and your private key, for example, they will keep it. You are the only one who knows, but they will keep it. They know, they store it, okay? And store and digital certificates. So those are the various components of any PKI. Now, the utilities have to do this. They have to have. And by the way, the companies, for example, ABB and Siemens, whenever they are supplying the equipment and all that, they are authorized actually as to keep this, right? They are the ones who are maintaining all this, okay? Okay, so how it is maintained? It's really an ongoing process, right? Uh, so certificate lifecycle management first verifies the identity and issues certificates. So we talked about that they are authentic organization. They will verify, and then renewal. Okay, depending on your requirement, certificates will expire. Okay, and they will need a renewal every 1 to 2 years. Okay, again, depending on the organization and the need and so on, right? And then if a private key is compromised, the certificate is going to be revoked. Okay, and you can actually discover whose certificates are revoked. Online certificate status protocol. Okay, there is actually a protocol that you can use and find out if how sometimes when you log in, try to log in and they say digital certificate is needed or something, the message comes, and that's what they're trying to verify, right? And then key management, we talked about that a little bit already. Secure generation, storage, and destruction of private keys. So if somebody is taken off, their private key need to be destructed also. So it's a management. Okay. So, and they use hardware security modules to protect the certificate authority keys. Okay. So, and then there is a policy and compliance. Okay. They have certificate policies and certification practice statements. Okay. And they are audited. Even certificate authorities are audited for compliance, whether they are doing their job properly, keeping, so that's how it is. right? So browsers and operating systems maintain a root list, okay, list of trusted root certificate authorities. They will maintain that, okay? And if a certificate authority is compromised, it's removed from there, okay? So any web browser, for example, Google or Chrome or all that, they have the list of that, right? And then obviously regular audits are happening. Okay, so when you visit, for example, when you visit, any HTTPS, which is secure site, okay, the server is going to send the certificate to your browser, and your browser is the one who is going to verify whether the certificate is signed by a trusted CA, has it expired. If it is valid, it uses the public key for secure handshake. Then you have maintained the link. That means it's secure now to talk to this particular site. Okay, so this is how the banks work. Okay, and in a way, the TLS that we will talk about, that SCADA system uses, also uses similar type of thing. Okay. Okay. So who designates certificate authorities? Okay, as I said, everybody cannot be. There is no single global organization that designates certificate authority. However, it's built into the software and systems by platform vendors. Okay, what we call trusted stores. So for example, operating systems and browsers. Okay, so your browser and operating system, okay, maintain their own trusted root certificate store. They have their own thing. Okay, that's actually a big thing right now. Okay, and root stores are basically certificates that are pre-installed. So when you connect to a secure site, your browser checks server certificate chain against those trusted, right? Those are already installed there. So those are again examples of the root store owners. Okay, Microsoft and Apple and Mozilla Firefox, all the big ones that we do. Okay, if a certificate authority isn't in these certificate, it issues won't be trusted, right? And for utilities, we talked about, I think later on I have. So how do you get into a root store, right? So apply to the vendor, apply to the web browser, undergo audit, and comply with the requirements, and then they will put you in the root store, right? So this is the certificate authority. So who oversees the rules, right? Again, there is no industry body, okay? There is a CA browser forum, which is a voluntary group, okay, which is a group of certificate authorities and browser vendors that define the baseline requirements. And then there are auditors like KPMG and Deloitte, right? And then there are root program owners, like we talked about Microsoft, Apple, and Google, and so on. Okay, so what happens if a certificate authority misbehaves? Then obviously their root certificates are distrusted basically, and they will be removed sometimes from their root store. Okay, so this is an example. Symantec CA was removed from Google and Mozilla for failing audits, right? So this is the certificate. But let's see if I have, how does it work in substation? So that was the basics, but let's apply it to the substation. I give you some examples, but let's take a look at a little bit more, especially the certificates. Okay, so we have digital communication networks. So we want to do authenticate the devices is really the correct protection relay. we want to secure the communication, and we want to support the regulatory requirements. So who needs certificates? Basically all the devices, right? IDs, RTUs, HMI, gateways, SCADA, and engineering laptops, right? They will need the certificate. So each device is issued a digital certificate that, we saw the structure of the digital certificate that has the public key into it, and it's signed by the certificate authority with their own private key, right? So that's the digital certificate. And each of these devices will have their own digital certificate, right? So what is the PKI model for substation, public key infrastructure? So who is the root CA? The utility itself, which is very rare, okay? They don't go there. So it's usually the vendor which will provide the private root CA, okay, certificate authority. And we see the what certificate authority does, those 6 things, right? So the root CA will sign intermediate CA, so the root's private key stays offline. So there is an intermediate certificate authority. So root, that's again another layer, right, to protect it, right? So, and intermediate CA is the one that issues certificates to field devices, and it can be vendor managed. ABB and Siemens could manage that, or it could be utility managed, right? Maybe larger utilities will maybe want to manage their own, certificates, right? So there are device certificates, okay? They will get a unique certificate, and I'll show you an example of a device certificate. And this is where it will be mainly used, TLS, okay? And also signatures, we just talked about that, on a goose or sampled values to some extent, okay? So how do you maintain that? What are the main ways? So it has to be operational technology environment is trickier than IT. See, sometimes people think that, IT can do the stuff. They can't, because operational technology is a little bit different than IT, okay? So this one has to be physically remote, okay? And we talked about legacy devices already, okay? So those are again the challenges, right? Because they have legacy devices which have no crypto support, right? You can't. And it requires very high availability comparison to IT, okay? You can't, for example, if you want to verify digital signature on a goose message, you can't wait. All this has to be available. You want to set up a link, secure link, digital certificate has to be available. So the availability is basically no downtime is allowed, okay? And then there are, rules and, for maintaining it, right? Sometimes you may install the certificates, pre-install the certificates, rather than trying to get it from central place. Your device can have a pre-installed certificate on itself. So it's always available, right? So, and you can, there are tools, uh, certificate enrollment protocols, right? Uh, for device, you have a new device, you can actually use some of these tools there, okay? And then certificates has to be monitored. So those are again very much common sense things. And the key management, so you can have private key right on the device, okay, provided your device doesn't have the password 12345, okay? So, and root CA are kept offline, right? So, and we talked about the revocation, and actually in substations and power systems, the lifetime of a certificate is shorter, usually 1 year. And this is where the big problem is. Sometimes they don't revoke the certificates. You may take the device offline, remove it, put a new device, but the old device stuff is still all there, right? So it's, and anybody can use that information and, do something in the system, because you haven't removed it from the certificate authority list. It's not part of the, revocation list, right? So what are the relevant standards? And these are the ones we will be talking about. Okay, 62.351. So tomorrow we will, after I give you the examples of that, that's the first one we will start talking about. Okay, and it will use all this information that we talked about: public key infrastructure, digital certificates, digital signatures, and so on. That's why I thought we should spend time on this, so that you will be able to better understand the standard, right? So we will talk about various parts, but part 8 and 9 are important. Okay, role-based access control, very, very important. What role has what access? And they will control it using the digital certificates. And also we will use the PKI for device authentication and so on, right? And then similarly, this is North American NERC SIP, right? Right. So this is again a quick. When you boot a protection relay, for example, it presents its XO509 certificates to the gateway. The gateway verifies the signature against the root CA using their public key, okay, and the device's roles and permissions at that time, right? If valid, then the relay is basically part of the system, okay? So even, that's why sometimes they store the certificate right on the device, okay, rather than in the, certificate authority storage, right? So this is just one example of how that will be done, okay? These are again between OT and IT networks, okay, main differences. Certificate lifetime, longer in IT, shorter, much shorter in the substations, okay? Connectivity, always online in IT, whereas often offline and air-gapped in the substations, right? Key distribution is automated. Here it's manual or semi-automated, okay? For security. And standards here, it's TLS at DTPS. Here we are going to talk about IEC 62351, and there is another one, IEC 62400 something. I forgot the number. So we will talk about those two standards. Okay, so they will designate their own CA hierarchy, often private CAs. Okay, you can set up your own, or you could. The good thing is that, if you are setting up your own, you are not going to, like Google, and you are not going to those people, right? You have your own setup, and you are using it for your own organization only, right? Right? Unless you are starting to use the web browsers in that, right? So again, depending on that, right? So again, connectivity constraints are there. That's the big thing. Actually, nobody has really done any work in that area on the connectivity constraints. Okay, so, and we will talk about this. The standard actually talks about how the key management should be done in power system equipment. Okay, and we will talk about that part. Part 9 of this standard talks about how you should do the key management. So now you know what are the keys, and what is the, but standard actually specifies how it should be done. Okay, And there is a little bit more about the standard itself, 9, but I think we are going to talk about this more in the standard. And if we need to come back, we'll come back to this one again. But let's leave it to the standard here. Part 9, we will talk about that. But this was the basics of PKI, public key infrastructure, encryption, decryption, digital signature, digital certificate, and then how these will be used in the utility and what are the standards and so on. That's what we will talk. So tomorrow morning, I'm starting, right? So we will do the, I'll show you the programs, so that you can get a sense of how, the real certificate looks like, digital certificate, how the real digital signature looks like, right? All that. So we will start with that and then go to the, I call it standards and solutions. All these standards for cybersecurity that are relevant to the substations and power system, and then some other solutions that you can use to cyber secure the system. Okay,